Welcome back, everyone. This is Dr. Gallenstein, and I'm back again for a quick lecture, kind of a follow-up lecture on the utility maximization lecture that I recently did. In this lecture, I'm going to talk about the indirect utility function. The indirect utility function. All right, and I'm just going to jump right into it. So here's the basic idea. When we do a utility maximization problem like we did in the last lecture, so let's say we were choosing coffee and bagels to maximize our utility, subject to the budget constraint. Okay. So let's say we're doing this. When we do this maximization problem, we are going to end up with the optimal number of cups of coffee and the optimal number of bagels that will maximize the utility subject to the constraint. Okay, so we're going to end up with this bundle. So now the question is, how much utility do I get from that bundle? Well, what we would do is we would take those values and we would plug them back into what we call the objective function. That we plug them back into the function that we maximized. Okay, now if you remember, when we maximize this function, we actually maximize the Lagrangian, right? Okay. All right, so we maximize the Lagrangian. So what we do is we take these values and we plug them back into the Lagrangian function. And what I'm going to show you today, all right, so actually let me just jump right into this. So we take the optimal values, we plug them back into the Lagrangian function, and then this function is going to tell us how much utility will be derived from the optimal values. Okay, and we call this the indirect utility function. All right, so then I am going to demonstrate this in today's lecture. But what you'll see is that when we plug the optimal values into the Lagrange function, what we get is the utility function with the optimal values. That these two things are the same thing. And this is the utility function at its optimal, and we're going to call this function here, we're going to call this the indirect utility function. I'm going to call this the indirect utility function. That is, it is the utility function at its maximum point. All right, so that's what I want to look at today. So I'm just going to get rid of some of this other stuff, and then we'll get right into it. Okay, so we're going to look at this indirect utility function. Okay, so our indirect utility function is where we have our utility function and then we plug in the optimized values. We plug in the optimized values. This is going to give us the max utility. All right, this is the max utility that is achieved given the utility maximization problem that we completed. Now, when we were solving the utility maximization problem in the last lecture, we noticed that the optimal values C and B were both functions of the parameters PC, PB, and income. PC, PB, and income. Okay, so then what we would find is if we plug these guys into here, what we're going to get is we're going to get a utility function that is no longer a function of coffee and bagels, is no longer a function of C and B, but is now a function of the parameters. This is the indirect utility function. Indirect utility function. It is a function, it is the utility function with the optimal values plugged in, such that now the utility function is a function of only the parameters and not of the variables. Okay, let's make that even more clear. Let's make that even more clear. So let me make the distinction. So we have the direct utility function. The direct utility function is the standard utility function we're used to. This function takes the goods as inputs, and it gives utility as an output. The indirect utility function is the utility function. Actually, sometimes we use the letter V when we're referring to the indirect utility function. Is now a function of just the parameters, not of the original variables. And this also gives you utility as an output, but it takes the parameters as input. So it takes the parameters as inputs, and it gives utility as the output. So what's happening here is that the direct utility function is a function of the decision variables. So the goods, or we might say the decision variables. Okay, so the direct utility function is a function of the decisions. This is really important, that it's the decision. That's why we maximize the direct utility function, because we want to find what the agent will choose. That means we want to know how many cups of coffee and how many bagels that the agent will choose. These are the decision variables. The direct utility function gives us a utility as a function of the decision variables. But then when we maximize it, when we go through the process of maximizing it, and we find C star as a function of the parameters, and B star as a function of the parameters, we end up eliminating the variables. Now that we have the variables purely as a function of the parameters, we plug that back into the utility function, we get the indirect utility function, which is now a function only of the parameters, not of the variables. Parameters are not chosen. They're not chosen. So when we maximize the direct utility function, what we're doing is we're looking at the decision variables. We are solving for the optimally chosen decision variables. When we plug those back in, now we have a utility function that is only a function of the parameters. That means this indirect utility function, what it does is it takes the non-chosen parameters. That means we're not choosing our income and we're not choosing the prices. We just take those as a given. So at any given time, I haven't chosen my income. I take it as a given. I don't choose the prices that I face in the market when I go to buy coffee and bagels. I just take those as a given. This indirect utility function takes those parameters as inputs, and it will tell me what the utility is just given the parameters. What it does is this indirect utility function takes the parameters, and it will give us the optimal constrained utility. It gives us the utility value that is achieved, assuming that the optimal constrained decision is made. So if we have the indirect utility function, we give it the parameters. That means we give it the prices, and we give it the income. It will tell us what utility is achieved given those prices and income, what utility is achieved at the optimal. So this gives us the utility at the optimal. Or we could say, assuming the agent chooses their optimal bundle at those parameters. Okay, so this indirect utility function is very helpful to us. We oftentimes want to let's say this. We want to study how would a change in income. Let's say we wanted to study how would a change in income affect the utility. How does a change in income affect utility? Well, first we need to know what their optimal decision is. So we do the utility maximization problem. We find the optimal choice of coffee and bagels as functions of the parameters, including income. We plug it in. Now we have the utility function as a function of the parameters. Now we can change income. We can look at what is the effect of a change in income on utility. So this indirect utility function is a very powerful policy analysis tool. We'll use it later in the course. Okay, so so that's kind of a little bit of an overview here. Let's take it into a little bit more detail and kind of demonstrate what we mean. All right, so let's do that. Now, to go into a little bit more detail, what we're going to do is I just want to kind of derive this. I want to derive this so you can see what this looks like, how we get this. Okay, so let's say again that we want to maximize our utility. Okay, and we're just going to use exactly the same function that we used in the last lecture. Okay, so we're going to maximize utility. We're going to say that the utility function here is just the natural log of coffee times bagels. Okay, and then again we have the same budget constraint here. Okay, so let's just solve this really quick. We're going to solve this really quick. All right, natural log of C plus natural log of B plus lambda income minus PCC minus PBB. All right, so we're just going to solve this really quick. Set it equal to 0, right? Because we're setting up the first order condition. All right. Oops. Okay, so we solve the first order conditions, right? PC, B is 1 over lambda CPB. Plug these in, if you remember from last lecture, plug those in. Yeah, let's go down here. So I'm going to skip some steps here. Over I. Okay. So what we're going to get here, C star equals equals income over 2 PC. B star equals income over 2 PB. And lambda star equals 2 over I. Okay, so here we go. Here are our optimal values. Here are our optimal values. Now, we've just maximized this utility function. We have just identified the value of, we've just identified the number of cups of coffee, the number of bagels, and then the Lagrange multiplier that maximize this utility function, or that maximize this Lagrangian function. Okay, so let's take those, and we're just going to plug them back in. We're going to take those, and we're just going to plug them back in. I'm going to delete all of this.
Okay, so we're going to take those and we're going to plug them back in to the Lagrangian function. Okay, so now we're going to have the optimal. Natural log of c, so it's natural log of I over 2pc, plus natural log of optimal b, so it's I over 2pb, plus 2 over I times I minus pc times I over 2pc. All right, I'm going to have to erase some of this. Minus pb over I divided by 2pb. Okay, so all I've done is I plugged those optimal values into the function. I've plugged in the optimal values into the function. I'm going to rewrite my c down here. Okay, so what I've done here is I've now plugged my optimal values in. Now, one thing that you're going to notice, actually, I don't think we need this anymore. Let's just get rid of this. Okay, so one thing that you're going to notice when you look at this function is you're going to notice, if you look at this whole thing, you're going to notice that there's no c, no b, and no lambda, right? So this thing is only a function of the parameters. So that means I can rewrite this as L of pc, pb, and I. It's only a function of the parameters. It is not a function of the variables. Why? Well, it's because we found the optimal values of the variables, and we found them as functions of the parameters, and we plugged them in. So now there are no more of the original variables. There's no more of the original decision variables here. So what this function is going to do is it will take these parameters as an input and give utility as an output. All right, so now I have a function of my parameters, not of my decision variables. Okay, excellent. All right, so now why don't we simplify this? Let's do some simplification. So first, let's put the natural logs together. Okay, and then let's do some simplification over here. First, we have I, okay, minus. Notice here that the PCs will cancel out, so you're going to get I over 2. Okay, and now the PBs cancel out, so again you're going to get I over 2. And so what's that going to do? What does this become? This just becomes, this all goes to 0. And so now this becomes natural log of I squared over 4 PC PB. All right, you're going to notice that this equals the same thing as if I had just taken the optimal values. So maybe I will write these back up here. 2PC P star I over 2PB. If I just took these two values and I plugged them right back into the natural log, I would get 2PC times I over 2PB. You multiply that together, natural log of I squared over 4 PC PB. Okay, so what we see here is that the optimal, so when you plug the optimal values back into the Lagrangian function, what you're going to get is the exact same thing as if you had plugged the optimals directly back into the utility function. All right, I alluded to this before, but now I've just shown it to you, I've proven it to you, and you'll have an opportunity to do that as well on the homework. But just to reiterate, I'll just rewrite it. I'm going to rewrite it. That if you plug the optimal values back into the Lagrange function, that's going to give you the exact same thing as you plug them back into just the utility function. And so therefore these two things are equivalent, and they are the indirect utility function. Okay. Okay, so there we have it. We have the indirect utility function. It is a function that gives us utility based on the parameters. It's a utility function that gives us utility based on the parameters at the optimal point. That is, considering the optimal decision that the agent would make. Okay. All right, so then let's go to the next step here, and let's consider, I'm just going to get rid of all of it. Let's start over. Okay, so let's just reiterate. If we did a maximization problem, subject to the budget constraint, we would solve that and get C star, B star. We could plug those values back into the utility function, and we will get the indirect utility function, which we might write like this, where it's now a function of the parameters. So now let's say that we wanted to know some things about how changes in the parameters might affect the ultimate utility that is derived by the agent. So this indirect utility function will give me utility taking the parameters as inputs. So this indirect utility function will give us the utility at the optimal. So then I might want to know, well, let's say, how does a change in income, let's say, how does a change in income affect utility? Affect utility at the optimal value, or at the max, Well, then I would want to know, what is the derivative of the value function with respect to income? Okay, well, let's look at that here. Let's try to answer that question here. And we're going to use that trick. We're going to use that theorem that we talked about in the last math review lecture, the envelope theorem. So let's just take a look at this. Let's say that I have my value function. Let's go here. Let's say that I have my utility function, C, B. Actually, let's go back. Remember I said the utility function. Let's go back to the Lagrangian. All right, B and lambda. Okay, so here's my utility. Here's the function that I optimized, right? It's the Lagrangian function. All right, so that is, let's just do it generically. So it'll be the utility function plus lambda times the budget constraint. Okay, so if I wanted to know, how does a change in income affect my utility, what I'm going to first acknowledge, what I'm first going to realize here is that income is a parameter in this function. So this is how we usually notate it, that the variables are first and they are separated by commas, and then the parameters they come after a semicolon. So here we have variables and then we have parameters. Okay, so then I want to know how does a change in income affect the overall utility. All right, so that means I want to know this. This is what I want to know. How does a change in income affect a change in the overall utility? Okay, if I wanted to know this at the optimal, that means I would need to, again, maximize this, so maximize this Lagrangian, right? Find my optimal values, and then take these optimal values and plug them back into the Lagrangian. Okay, I'd have to take these values, plug them back into the Lagrangian, and then end up with a Lagrangian function that is a function purely of the parameters. And as I just showed you in the last solution, that this would be equivalent to the utility function at the parameters. Okay, so that's what I would have to do. I'd have to solve all of this and then take the derivative of that utility function with respect to I. If I wanted to do that, that's how I would have to do it. All right, if I wanted to know how does income affect the utility, I would have to go through all of those steps. But now let me show you a shortcut. Okay, let's show you a shortcut. So let's assume that we've already found C star, B star, and lambda star. Let's assume we've already found that, so we plug that in, and so now we have the Lagrange function at the optimal, and so it is composed of, actually, let's write it out this way. C star, B star, lambda star, and then it has this parameter I. Now I want to know what is the derivative of this with respect to I. All right, well, let's keep it generic and let's do the total derivative. Let's do the total derivative. If we did the total derivative, what we would end up with, so total derivative, remember, C star is a function of the parameters. B star is a function of the parameters. Lambda star is a function of the parameters. Okay, so then if I wanted to take the derivative of this with respect to I, we're going to need to use the total derivative. The total derivative. So let's use the total derivative here. That means I take the derivative of L with respect to C star times the derivative of C star with respect to I. And remember, this is a series of chain rules. I need to take, because C is a function of I need to take the derivative, I need to treat this like a chain rule, where the outer function is L, the inner function is C. So, if I want to know the total derivative of L with respect to I, I've got to do the chain rule here. I've got to do the chain rule with respect to C, because C is a function of I. Then I need to do the same thing for B, because B is a function of I. So the derivative of L with respect to B star times the derivative of B star with respect to I, plus derivative of L with respect to, so I got to do the partial, I have to do the chain rule again with respect to lambda star, because lambda star is a function of I. All right, derivative of lambda star with respect to I. But then also, we will see that the original function is itself a function of I. So that means we need to include the direct derivative. The direct derivative of I. That means the derivative just from the original equation. Okay, so these are all chain rules. So do the chain rule a bunch of times. Right? And each of these terms is a partial derivative. And then this is the direct derivative. Okay. Now if you remember from our discussion of the envelope theorem, that the envelope theorem says, I'm just going to write it up here. Let's do this. The envelope theorem says that the derivative of a function at its maximum with respect to a parameter is just equal to the direct derivative. Actually, I'm going to put a star down here to symbolize that that is at the optimum. So the envelope theorem says that the derivative of a function at its optimum with respect to a parameter is equal just to the direct derivative. So that means if I want to know how does income affect this optimal utility, I don't actually have to do this whole monstrous total derivative. I only need to do the direct derivative. And why is that? Well, it's because at the optimal, the derivative of L with respect to C is equal to 0. The derivative of L with respect to B is equal to 0 at the optimal. The derivative of L with respect to lambda star is at the optimal is equal to 0. This because these are first order conditions. These are the first order conditions from the optimization. And so those are all equal to 0, which means that we can use just the direct derivative. Okay, so with all of that said, let me just do it in practice to show you what I mean. So let's say that we started, let's just erase all of this. So let's say we started with this equation and we wanted to optimize it. All right, so we maximized this. We found C star, B star, and lambda star. All right, so then let's plug those in, C star, B star, lambda star. It's also a function of I. Now I want to know the derivative of this with respect to I. And I look at this, so this is the star, this is the optimal. I look at this and I say, man, this is really complicated because C is a function of I, B is a function of I, lambda is a function of I, and the L function itself is a function of I. So it looks like a very overwhelming, derivative. However, by the envelope theorem, we know that this is just equal to the direct derivative. Well, what's the direct derivative of this expression with respect to I? It's just lambda. If I take the direct derivative of this, basically I ignore the fact that C star, B star, and lambda star, I ignore the fact that all of these are functions of I ignore that, and I just take the derivative with respect to the I that's in the original equation. That, if I just do that, then I can see that the derivative of L star with respect to I is equal to lambda. So basically, I just use the envelope theorem to make my math a lot easier. Because it becomes quite easy for me to ask a question of, okay, how will a change in a parameter affect, how does a change in a parameter affect an agent's optimal utility? Well, I will just use the envelope theorem to determine that. And so let's say that I wanted to ask the question, how does a change in the price of coffee affect total utility? Well, this will be equal to the direct derivative. What's the direct derivative? The direct derivative would be negative lambda star C star. So this is the impact of a change in income on utility. This is the impact of a change in price on utility. Okay, so basically we can use the envelope theorem to substantially reduce the amount of calculations that we have to do if we wanted to predict how a change in a parameter would affect the total utility, the total maximized utility. Okay, so then let's take this this calculation, this demonstration. Let's take this as an opportunity to also just discuss. Let's take this as an opportunity to discuss the economic intuition behind this variable here, lambda. Let's take this as an opportunity to discuss the economic intuition behind the variable lambda. I'm going to delete some of this. So we haven't really talked very much about what this lambda variable means, but it comes up. We could just ignore it, but it actually has kind of an interesting economic meaning. So this lambda, what I've just shown you is that if I wanted to know how does income, how does a change, so let's just write this out, how does an increase in income affect optimal utility? How does a change in income affect optimal utility? Well, I've just demonstrated how to do that. All right. So optimal utility, that means it's L evaluated at the optimal values of C, B, and lambda. Okay. So I want to know, how does the income affect that? Well, I take the derivative of the optimal L with respect to I, and I'm just going to get the direct derivative, lambda star, and I might write by the envelope theorem. That means I used the envelope theorem to do this calculation. Makes it much, much easier. Using the envelope theorem makes it much, much easier. Okay, so how does an increase in income affect optimal utility? Well, it affects it by lambda. That means this is going to have some economic intuition that's interesting. What does lambda stand for? What does lambda stand for? Well, we can actually, we can intuit the economic meaning of this variable lambda. Why? Well, I say, well, how does a change in income affect overall utility? Well, it changes it by lambda. It changes it by lambda. So let's try to interpret this. So lambda is called the shadow price. All right, so sometimes we'll call lambda is the shadow price. It's the shadow price of the budget constraint. What do I mean by shadow price of the budget constraint? Well, let me elaborate. Lambda is the utility value of relaxing the budget constraint by 1 unit. Okay, so what does lambda tell us? Lambda tells us the utility value. Lambda gives us the utility value of an increase in income. And that's another way of putting it, is lambda tells us the utility value of relaxing that budget constraint. That is, if you increase your income, what you're doing is you're relaxing the budget constraint. You're making the budget constraint less binding. So lambda is this measurement. Lambda, so if I say the shadow price, lambda is basically the price in utility terms of your budget constraint. Lambda tells us how much it costs you in terms of your utility. It's the, or we can put it another way, it's the marginal value. It's the marginal value of income in terms of utility. So if you were to increase your income by 1 unit, lambda is how much your utility would go up. If you reduced your income by 1 unit, lambda is how much that would cost you in terms of your utility. And so therefore lambda is a price. It's how much your budget constraint costs you in terms of utility. It's how much utility you lose if your income goes down, making your budget constraint more binding. Or it is the amount of utility you gain if your budget constraint, if your income goes up by 1 unit. How much? So it's basically the utility value
of that budget constraint. Okay. Okay, that will be it for today's lecture. In the next one, what we're going to do is we're going to take a look at expenditure minimization. All right, have a great day.